Okay, I guess I'll start up now. My name is Steve Rostedt. You can see the thing. I don't block it, so I actually can walk in the middle of the screen now. I work for Red Hat. I just always say Red Hat's the one that pays me to do as my hobby, but now they tell me to do things more, so I can't really say I actually have to work now. I've been with them for almost 10 years. I started working on the real-time patch. Before that, I worked with TimeSys, and then I contracted, but then I started working on this as trying to get Linux into real-time, and I looked to see if anyone was doing it, and I noticed that Ingo Molnar had a project called Preempt Real-Time. And I jumped aboard and started working back in 2004, and then they changed it to the -RT patch. Since then, Ingo has passed off the maintainership off to Thomas Kleichner, who's here. And if I don't see him around, he might stop by. Tall, German, scary dude. And I've been working with it for some time. Thomas Kleichner is in charge of the development of new changes or getting the latest kernel up and running with the real-time Preempt RT kernel. I maintain the stable releases, so when a new kernel comes out and Thomas decides to work on that new kernel, he passes off what he has done on the previous kernels to me, and I maintain that all on kernel.org. There's plenty of spaces you can fill in. So what I'm talking about today is actually not about the real-time kernel, although I will mention it because I've given so many talks about the real-time kernel and talked about it, but right now I'm more interested in what a real-time system is. So understanding the real-time system, more than just a kernel, is my talk. So what is real-time? Now, I want to get a feeling. I mean, does people know what real-time is? Or I'm going to go over and don't raise your hands. I know everyone's just came back from lunch and they really don't want to say it. Like, I don't know. Everyone does know, right? See, no one knows no. So anyway, I hate the term real-time. I watched the Microsoft talk. It was actually very interesting about the real-time going into, I don't know, is the guys here? The Microsoft guy here? It was a very interesting talk, but it was about real-time in an aspect of, I always like say, live streaming. You get to see things as it happens. That's a different terminology. That's not what I'm talking about. I'm not talking about that, as things happen, to see things happening at real time. That's not what this is. Real time for us means determinism. So it's always, I hated the misnomer of real time because people also think real fast. Real time, real fast, that's not true either. I'll talk about that later too. But people think about real-time operating systems, RTOS. I hate that. I always want to call it a deterministic operating system, DOS. Which is a very real-time operating system. It does exactly what you want to do, when you want to do it. If you make it crashes very nicely. So what is a deterministic results? Basically, it's repeatable. You could predict what's going to happen. You say, it's going to take 10 microseconds to do this. It takes 10 microseconds to do this. Or you get a range. Or it will say it will never take more than 100 milliseconds. And it never takes more than 100 milliseconds. If it does, it's a bug. You got to fix it. We look at worst case scenarios. Unbounded latencies. I'll talk about that later too. And when you deal with real time, everything that you deal with has to be predictable, deterministic, because if something in your system is not real or is not real time deterministic, your whole system will fail. So what is real fast? A lot of things in computers make things go real fast. Reason why is because 90% of users want throughput. They're interested in getting things done as fast as possible. And I gave a talk in Brazil once called, real-time kernel, who needs it? Not you. Because most people don't really care about determinism, they care about speed. And a lot of times, determinism is sacrificed for speed. And here's the things, you have caches, look-ahead features, saying like, okay, we're seeing a thing, we know that in this pattern, most of the time, we go in a straight line. We don't do jumps or whatnot, so we'll start fetching stuff ahead of time. And that speeds things up. Paging, if anyone uses an MMU, I know here there's people that don't care about paging because they use MMU list systems, but I'm not talking about you guys. That's a boring process. As Lena said earlier, it's not interesting to them. Although I laugh because in my old days at TimeSys, my first project was to port Linux to an MMU list MIPS processor. So it's actually quite fun. But paging, you have the page tables, and you have something called a translation look-inside buffer, which is basically cache for your page tables, and I'll talk about that as well. You don't want interruptions. You want to batch things. This is to make things real fast. If you run something for, say, 5 minutes, if say you have a bunch of jobs that run at night, and you want things to be done at, fast, you can run something for 5 minutes straight, and that process will have total control of the CPU, it'll have total control of the cache, and it will be very fast, but yet you have no reaction time. If something else wants to come in, it's going to be very slow to switch to that. So that is, again, something that's real fast that actually hurts your determinism if for other things to work. Optimizing the most likely conditions. There's something called transactional memory that's coming out. And that's an interesting feature because anyone here knows what transactional memory is? Okay, a few people. Basically, the way I do it is, say if you have a lock. This is what the kind of overall, general, not detailed process, but just the general scope. Say if you grab your lock, you go into a critical section, and you just run without ever taking the lock. You don't do any memory locking, or you don't do because to grab a lock, you've got to synchronize across CPUs to make sure everyone else is fine with that. So you kind of ignore that, but the CPU knows about the lock. So you jump in here, and if you could finish that critical section and no one has touched it, you're fine. But say if you're about to finish it and someone else comes into the critical section, well, you kind of fall. It goes back, takes everything back that you did, all the transactions, all the way back to what you started, and you start again, which is fast most of the time, but can be really, really slow or non-deterministic. So it's a balance that we have to make. There's real time versus real fast. We want things to be real fast and real time. So even though we sacrifice stuff, we work really hard and jump around and make hoops to make sure that we have a system that is usable. I mean, if it's very deterministic, but every key you press deterministically takes 20 seconds to show a character out, you're not going to use that. But it's real time. Yeah, because people don't realize that. That's why I'm saying, to give you an idea of how fast. If you type and it takes 20 seconds for a character to pop up, but it won't take 21 seconds, it always takes 20 seconds, that's a deterministic operating system. It's a real-time operating system. It just sucks. So, to understand the system, everything has to be real time. It has to be the hardware that you use, the BIOS that may jump in to use it, the kernel, which is what I work on. Your library has to be aware of it, and your application has to be aware of it. And as you see, the library could skip the kernel and get into the hardware, can touch the hardware. The application could go use the library to get to the kernel, or it could go to the kernel directly, or it could go to the hardware directly. So everything has to be aware. If you make a real-time system, every aspect of your system has to be aware of this. So I'm going to start from the ground and go up. The hardware, the foundation. Like I said, if it's not deterministic, forget it. We had this time, this guy on IRC showed up. By the way, if you go to OFTC, pound Linux-RT, that's where we hang out. And we seldom talk about work. It's our water cooler kind of IRC thing. We sometimes talk about work. But this guy shows up and says, I'm seeing latencies of 500 microseconds, actually a millisecond latency. It's like 2 or 3 millisecond latencies on cyclic tests, which is our test. We have a little program that we write that does loops and checks the jitter, how long, when it's supposed to wake up and when it actually did wake up. And this guy was seeing maybe 5 milliseconds latencies. I'm like, this is insane. So we were helping debug this, helping check this code, do dmessage, do this, do this, do this. And then something I noticed was, wait, what exactly are you running this on? Because I noticed this is like a virtual machine, isn't it? Yes, he was running it under like VxWorks on a Windows box. I said, you know what? I declare you the maintainer of the real-time patch on VxWorks on Windows. So yes, what you run it on, just because this guy really thought that if you threw a real-time operating system into a VxGuess on Windows, you would get real-time responses. It doesn't work that way. That's pretty obvious. So we have memory cache, branch prediction, NUMAs, server threading. You can read. I don't think I need to read it for you. Or if you want to sleep, I can just... so you close your eyes, I'll say it. Hyperthreading, TLB, transactional memory, SMI, CPU frequency scaling. By the way, I've been told I could kind of talk a little fast. So memory cache. Memory cache is a wonderful thing because it helps speed things up, but also it's this time bomb waiting to go off. So if you want to know if you can get your worst case scenario, and part of real time is understanding that you can make your deadlines, that you want to see predictable results, but you need to find out what is the worst case scenario, and you start writing code. You got to try to run things on cold cache. You could try, there are ways to turn the cache off, but remember I said about typing something and 20 seconds later your thing shows up? That's basically what happens when you disable cache on your hardware. But then there's time that you could have a race condition that you don't know about, and, well, you're just out of luck. Sometimes you just can't win. You know, real time is hard to do, and I try to tell people think, oh, I just throw the real-time kernel on here, and I have this, and I don't have to worry about anything else. It'll just work for me. No, you have to understand the whole system because your application must be aware as well. But in most cases, if it works under cache, it will work faster. And what I meant by that race condition things is if everything's slow, you might not hit the race condition, but as soon as you make the cache jumps in and things go fast, the race condition could hit. Anyone here see the Sched deadline talk that was there? Yes. Great, that's coming up. Where is he? Is he here? I don't know. Okay, he missed my talk. I came to his. I'll get back at him. Anyway, I'm testing the deadline scheduler. That's what I'm working on right now. That's why I haven't been doing much with the ftrace work. I'm working on making sure deadline scheduler works, because that's going to be the future. And I wrote a tool, and I traced it, and I saw this. If you look at it here, I have two tasks running. One runs a little faster than the other. This one does so many loops. It's actually calculating prime numbers. That's what it's doing. And this one's calculating prime numbers as well, a little bit longer. It says, OK, I want you to do so many calculations. This one does like X many calculations. This one's going to do Y calculations, a little bit more. But then I started seeing this. Small, small, long. Like, see that? Long, short, short, long, short, short, long. It's kind of Morse code. Long, short, long, short, long. I'm like, what the hell? Well, I forgot I did something wrong. It was using the same variable to count, like to look at the prime numbers. So it was updating the prime. Both of them were updating prime numbers. This is two processes slamming the cache line. And it's this very good visual to see that when these two guys are like hitting, you get a lot of, there's back and forth cache, what's that called when, thrashing, yes. The cache thrashing. Look how much different, it's almost more than twice the size in time when that happened. So you got to be aware of that. Branch prediction's fun. This is another little gotcha point. CPU recognizes how the flow of your program is going. And it will try to remember that, hey, this guy always jumps here. So while the processor's reading the pipeline, and it sees branches coming up, it could start fetching. It says, well, you branched for the last 20 times you branched here. I'm going to now fetch where you branched to and not fetch what's beyond the branch. But what happens when it changes and you go straight? Well, you just hit cold cache and everything comes to a halt. You pull in the memory. The CPU has to work harder. Everything kind of basically halts until the memory gets loaded up into the cache and you can read it and continue. So branch prediction is another gotcha on trying to figure out how your worst case scenario is. So case in point, I had this one test line. Before I did the prime numbers thing, I did a get CPU system call into the kernel, and I was just doing a bunch of spins in the kernel because it seemed to be a slow operation. I could keep the count down less than a million to get like a millisecond worth, and it was weird. Sometimes it would pass all the deadlines, make all the deadlines, but then it failed all the deadlines. And I'm like, what the heck is going on here? So I ran perf on it, and on the good time, like I would record it and see if it made everything, and then I cut and paste it, and then I ran it perf again on when it failed. I kept running until it failed, and I took it, and then I looked at the things, and I noticed this. Right here, branch misses, we have 798,000 branch misses on the good one. On the good run, the CPU only failed to predict the branch 798,000 times. On the bad one, 4 million times. By the way, I also found out that when I was doing this test, I had the branch profiler enabled in the kernel. So it really exaggerated this point. But it was really good to see why one way it worked fine, and then suddenly the CPU decided to fail it just was doing a bad job at prediction, and it slowed the system down it was like about a good 20 microseconds, 30 microseconds slower when this happened. But it was just on that edge where it popped out. Maybe closer to 50 microseconds. Another thing you want to talk about is NUMA. So, everyone familiar with NUMA, or most people? Okay. Basically, what NUMA is, just for I don't want anyone here saying, "Oh, I don't really know." It's a large CPU. Like a machine has lots of CPUs, and you can't have, there's space on how you make everything interact with each other. So a lot of times you have a group of CPUs that have memory here and a group of CPUs that have memory here. They all can see all the same memory. The problem, though, is if this CPU tries to go and access memory across the nodes, because now you have nodes of CPUs, okay? And each node has a memory that it's really fast to, but if you try from one node to get to that memory, it's slow. So you need to be NUMA aware when you do this. If your system works fast because it's running on the same, or if you have a large-scale system, of course it's embedded in Linux, but you don't care about NUMA. So if you have a process that's running on the node and it's using the memory for that node, and then suddenly you run it again and it gets loaded differently or migrated to another node, and it's using the memory from the other node, and suddenly you're dropping all your deadlines. That's why. It takes a long time. Things slow down. You got to be aware of this. It's interesting because one of the things that Red Hat supplies is something called RT-eval. And what it does, I don't ever use it because I mainly do what it does, is it runs cyclic tests, and which is, like I said, it checks the jitter. Then in the background, it will kick off a kernel compile in this tool called Hackbench. Are people familiar with Hackbench? If not, search for it, Hackbench. I think Rusty Russell is the one that wrote it. It basically creates a bunch of pipes. It stresses the scheduler big time. It creates a bunch of pipes and has all these tasks, piping information back and forth, and it does it for a long time, and it really stresses the CPU a lot. So we have a strong stress of the CPU going on while we're running cyclic tests under a real-time, and it better not miss latencies. Well, one time we were testing this one box that had 64 CPUs, and it was failing latencies. And whenever we ran Hackbench, it would just fail miserably. And I was trying to find out what was going on. Well, I found out what happened was Hackbench is an application that shares resources across all the threads. And Hackbench will basically fill up all the CPUs as much as possible with processes that are going to slam each other. And they're all sharing same resources within the kernel. It's opening up a pipe, a single pipe or something, so everyone's slamming this, or a socket. It would say open up a socket, and everyone's slamming the single socket that's shared across all the kernels. Well, think about 68 CPUs. And we had a spin lock that's only held for, they say, 1 microsecond. Well, think about that. You have a spin lock that's held for 1 microsecond, it was grabbed twice. And we found out there was conditions where if that 1 microsecond held, well, it made it worse. It was held for 1 microsecond, but it blocked on it, and because it was the cache thrashing of everyone nailing this one spin lock, it was a real spin lock, not one of these sleepable ones, and it went across all CPUs, across all NUMA nodes. And it was dramatically slow. Actually, some of them took like 100 microseconds to grab that spin lock because it was sharing it among all the CPU nodes. And I told our developer, Clark Williams, our task lead, I said, bring it down. I'm curious. Let's run off a bunch of hack benches instead of just one hack bench that goes across all the CPUs. Kick off one per node, so they don't cross nodes. And we did that, and the system passed with flying colors. So I think what we're coming now is we're changing our requirements and saying that, you know what, that's not a real case scenario. Yes, we're stressing it. We want to see determinism. But if you have a 64 CPU box and you have a process or a bunch of threads that's going to share kernel resources across all the nodes, we're going to tell you that's not going to make your that will not make your system predictable, or you will not make your deadlines. You're not going to make our 100 microsecond guarantee of jitter. That will not happen. So we're changing the requirements to fit the situation because there's no way to solve that. Like I said, 1 or 2 microseconds that went across nodes just doesn't work. Hyperthreading. There was a time where I was running my tests and I was getting really unpredictable results and I couldn't figure out why. It was on this laptop and I had hyperthreading on. And I'm like, I forgot I had hyperthreading on. Now what hyperthreading is basically it's an Intel feature. You have basically 1 execution unit, 1 system bus, 1 cache, 2 sets of registers, 2 sets of CPU pipes. And so the execution engine, what it does is it says, okay, when I'll work on 1 set of 1 pipeline, and when I need to go fetch something and I have to waste it takes a few cycles, I have to wait for the memory, I'll go work on the other one. So it looks kind of like this. You have your 2 registers, your 2 pipelines, the engine, the same single CPU cache, and so it's running, and when it gets a stall, it'll jump over here. But you have no idea when those switches will be. So very unpredictable results with this enabled. I always tell people, if you're using a real-time environment, disable hyperthreading. It's just going to make things unpredictable for your test cases. Transactional look-aside buffer, the TLB. Now, the way the pages work, I'll just give a lot of people know this already. Page tables I'm just going to kind of focus on Intel. So other architectures do it slightly differently. It's mostly the same. I know when I was working with PowerPC, you had the BAT registers. Batman. Inside joke. So basically, page tables you have your memory layout. For those, I'm going to quickly tell you so people who don't know what page tables are used. Say you have an address you want to access. Well, this is a virtual address. So some space, you have all these numbers in the air, and they got to map somewhere. It could map to memory. It could actually map to a device. So how does the CPU know that this number maps to some device? So because you also have the physical address for your memory is hard-coded. That doesn't change. But if you have 4 applications running, you don't want to have to allocate different locations. So you have virtual memory, unless you have the MMU-less not fun thing. So you have your page table. It takes the first few numbers, and it will index the first page table in the physical memory, usually. Then the next set of numbers will find out in the next page table, and then the next set will find you where this memory actually is mapped. So you have some virtual address maps down this. But this interaction here takes time to do for the CPU. So to speed it up, you have the TLB, which is basically a cache for the page tables. So when you get that number, if it's already been used, it's already been calculated, it says, oh, this number is going to map right to that page. It's a quick way of doing things. Well, guess what happens when, if you run your system over and over again and everything's in the TLB, your system will be really, really fast. But then you run it with something else coming in, it flushes the TLB. Next thing you know, your system's not working like you want it to do. So that's what you have to worry about. I mentioned transactional memory. Like I said, allows parallel things to happen almost in critical section. As long as no one touches anyone else's memory and stuff like that, you're fine. But if you do, you're screwed. You have to go back. Again, another non-deterministic action. Transactional memory is horrible for real time. My favorite, the SMI monster. Your system monster mode. What SMI is usually your software. Remember that little black BIOS thing I mentioned you saw all there? Well, that's your firmware for your hardware. So your laptop doesn't always have hardware that's going to figure out when to turn your fan on. That's actually done in software. But it's not software in the kernel, because what happens if you have a bad kernel? It doesn't turn your fan on, now your laptop melts. You don't want to do that. So the hardware, the vendor, Lenovo here wrote the firmware, or maybe they've hired it out, whatever, got firmware, or someone to write the firmware that says, periodically we're going to take an SMI, which basically is a way of telling the kernel what you wrote, what we write, to stop. Let's go look, jumps to some code within the firmware, and it's going to execute something like, how's the temperature? Should I turn the fan on? Should I make it slower? Should I change the speed of the CPU? So that's what SMI does. Well, you think that's predictable. And especially when we're doing test cases on machines, and we run the RT eval that we run. I told you about the cycle test and all the stress we do that for 24 hours to see how it can't break that 100 microsecond time throughout that whole 24-hour run. Suddenly, what happens is we get this huge 500 microsecond latency. That happens. We have a tool called hardware lat detector that will spin in the kernel that could detect this data. And actually, what we found out in this one system, that every, 45 minutes, we got this appear 500 microsecond gap in the spin. We found out that it was running some ECC memory correction utility every 45 minutes for some reason. The hardware vendor forgot about it because we were turning everything off. We were talking to them like, why is we doing this? And they're like, oh no, it's your fault, it's your fault, it's your fault. And we finally said, no, we ran the hardware landscape. The kernel is in idle running a spin and we have a gap exactly every 45 minutes. That sounds like a hardware thing to me. CPU frequency. Again, now this isn't really real fast things, but power saving is another thing that's detrimental to real time. A lot of times I tell people the best thing you do if you want a real-time system is idle equals pole, which is up your AC quite a bit if you do that. You have a nice little space heater next to you. You can sit on your laptop and it will be a nice cushion warmer. What idle equals poles means that the system will never slow down and it will spin like crazy and it will get pretty hot. Which I want to talk about SMIs. I've had people that go onto their laptops and disables all their SMIs to run real time. And I tell them no, because what happens is their system burns up and dies, and they have to go get a new laptop. So if you're trying to make a real-time system on your laptop, you don't turn off all your SMIs. Because I said, that laptop does a lot to make sure that thing's cool in that small confined space. So beware. Now, I've turned off all the SMIs once, but what I did was there also another feature was set my fan speed to max. Doesn't do anything. So when this thing burned up, it sounded like well, it wasn't this one, it was my other laptop that sounded like a jet engine when it started and stayed like a jet engine the whole entire way because the fan was just blowing. But I just had idle equals pole and it was burning up like crazy, but the fans kept it cool, so that worked. Your mileage may vary, so if it crashes and dies, don't tell me. Don't come back to me. CPU idle. Here's another thing you have to watch out for, is if your processor goes to sleep, it may take a little bit while to come back out of it. I'll talk about that. With the kernel. If you want a kernel, you need a real-time kernel, and preempt RT patch makes Linux into a more real-time kernel. I've given talks about how we do that. It's beyond the scope here. But things that are visible to the user, I'm going to talk about. Things are threaded interrupts, which is a mainline. Our system management threads, which has more system management threads in our real-time kernel than we do in mainline. High-res timers is in mainline. By the way, these are things that came from the real-time patch for a long time that made it into mainline through us. In fact, we've been told that Linux is now a soft real-time system due to the real-time patch, by the way, which is not a soft real-time, it's hard real-time design. CPU isolation, another thing. Then there's no hertz and no hertz full you need to be aware of. Normal interrupts that you have is the hardware, your CPU is going along, you hit a key, the keyboard is going to send a signal to the CPU that's going to trigger an interrupt, and the interrupt will stop the system from doing whatever, and then it jumps to the device driver, and the device driver has a function that's going to handle that key and it's going to read something and do some work, and then it will return back to your showing of whatever task you were playing. A lot of times, this could take a long time, and it's not deterministic. A lot of these drivers, especially your hard drives, could take a real long time. You're talking about milliseconds. So you can have a millisecond latency due to an interrupt. It shouldn't, but it can. So we have things called interrupt threads. And what happens, what an interrupt thread does, the hardware interrupt still comes in, but all it does is says, OK, wake up a thread handler to do the work for you. And then it will return back to the system. And also it disables the interrupt of that device, either the device or the device line, depending on how your system's configured. And then you can continue your task, and it only got that little gap right there is all that your latency was. But then you continued, and when you're done and you go to sleep, the device driver can now wake up and run. So with threaded interrupts, you can now prioritize interrupts. You can make one interrupt higher priority than another. You can make your task higher priority than the threaded interrupts. So I had someone do this once where they did a polling on the network interrupt, but they had their task at a higher priority than the network interface. So the interrupt would come in, the wake up, if you go back there, you know, the task is running, polling, and the interrupt came up, wakes up the network device, and then it goes to polling again. It never slept. It never went to sleep. So the network, what it was waiting for was spinning. And they're like, why is my system locking up on me? It's not doing it. Like, well, you need to up your interrupts. This is why I said you need to be aware of the interrupts that are happening. And I talk a hell of a lot because I just hit 10,000 with my hands. I talk with my hands, and that counts for my Fitbit. Anyway, going back to, I get sidetracked a lot. Going back to my interrupt handler, which I forgot what I was talking about. I'll go back to thread interrupts. It vibrates. Does anyone know what operating system's on this? Tell me later. Like I said, don't pull. So like I said, know your system. Soft interrupts. Here's something else you have to be aware of. In the mainline kernel, not with the RT patch or going on to it, you have a soft interrupt. A soft interrupt is still an interrupt context. It still will stop it's higher priority than any task. It's just lower priority than actual hardware interrupts. A hardware interrupt will come in and trigger and run with the interrupts disabled and do some tasks. But it could raise the soft IRQ, so when it returns back, instead of going back to your task again, it now runs another handler that does a little more work, but it has interrupts enabled. So if another interrupt were to come in, it won't stop other interrupts from coming in. If it does too many soft interrupts in a row, it will say, hey, we can't stay in here forever because the tasks want to run. It will just postpone it to something called ksoft-irqd, and that thread will wake up and finish the work for you some other time. That's how it works in mainline. With the real-time patch, with the networking code, what happens with the networking code, when your network packet comes in, it will wake up and take the packet and put it on some queue, and then it lets the soft IRQ run the rest of the networking code. Well, our interrupts are threads, but what we do is we have to figure out soft interrupts. We have to be careful about how we handle soft interrupts. What happens with the real-time task is when a soft interrupt wants to be raised by usually a hard interrupt or whatever or not, but it's usually done now by a hard interrupt with the thread. It's going to raise that soft IRQ, and when right there, it's going to run that soft IRQ handler. If soft interrupts or soft IRQ are disabled at that moment, which they usually are with the interrupt handler, it's going to be deferred until they're re-enabled. Then that task, the task that raised it, will run the soft IRQ. Now, if the soft IRQ is raised an actual real hardware interrupt, which some things do, it's going to be delayed to the ksoft-irqd, which still exists. Like I said, and those are for like RCU timers run into the case, like a RCU triggers a timer interrupt, a hardware interrupt, and says, okay, we have to do some RCU's work, and that's going to be delayed into the ksoft-irqd to run that soft IRQ processing. So you have to be careful about starving that. I want to actually go back one more time about this thing I just discovered because I had to send patches to the real-time patch. We discovered this on Red Hat, was that we had the system that does polling. Goes into polling mode in the networking packets. Different than the story I told you, but what happens is when the interrupt comes in from the network, it would raise the soft IRQ. But we were doing this test that we stressed the network out. And then, so you had this high priority networking thread would execute, receive the packet, because it's in polling mode, and then it would kick off the soft IRQ, which because, like I said, it runs it itself, so it would run the soft IRQ handler, another packet would come in. And when it came back, it says, oh, we got another packet, let's run that. And then another packet came in, let's run that. Well, we have now this real-time task running forever. So it's basically locking up the system because it's not going anywhere. It locked up that CPU. Although it was fine because that CPU was dedicated for the networking. So you think, what's the problem? You have a task that's running in the kernel, spinning forever. If it was user space, we have ways to handle it. But because it was running in the kernel, it stopped RCU from going on. So RCU came to a halt. And now other systems require, I'm not going to talk about RCU, that's another talk, but it requires that all CPUs report in eventually. And what happened was the CPU stopped reporting in. And when someone else tries to synchronize some RCU work, it calls something like synchronize RCU, which is going to wait until all CPUs report in. Very high level, it does a lot more than that. So because this one CPU wasn't reporting in anymore, it stopped. So synchronized RCU is called quite a bit in the kernel. So every time that was done, it stopped, it stopped, it stopped. The next thing you know, you have a system that's just hung. It's not doing anything. So and that was because the packets keep coming in, and it kept processing it. But as soon as you stopped the packets, the system came back again. So that was not a good thing, and I have a patch for that hopefully I have to talk to Thomas to get it into the real-time patch. So system management threads, you got to watch out for your RCU, your watchdog, migrate, kworker, ksoftware, RQD, because if these guys starve, bad things can happen. POSIX CPU timer is another one, which I think I talked about. Yes, timers. Now, if you use set iTimer, which is a system call, it runs under ksoftware RQD. So if you have a system that's going to pull and starves ksoftware RQD, or it's waiting for this timer, if you set iTimer, ksoftware RQD is what's going to handle that timer for you, and if it never runs, your timer will never come in. So that could block you as well. Timer create and timer set timer, the POSIX timers, and instead of using ksoftware RQD, it has its designated POSIX CPU timer thread. If you have the real-time patch, you'll see POSIX CPU timer thread. Make sure that has a higher priority than anything that requires using it. And it uses the high resolution timers, I mentioned that. But you have to be aware, it uses signals to deliver the package. So if a timer goes off, it's going to send a signal to you, and that has a lot of work to process signals. The signals have an issue on their own. I'm sure people who develop it. CPU isolation. It's funny, it's the preferred method that's no longer preferred. I was reading the documentation, and it says this is the preferred method of doing CPU isolation. Use ISO CPUs on the kernel command line, like 1 through 3. It's going to keep everything off of that CPU. Today, if you talk to Peter Zilstra, he says, don't do that anymore. But if you read the documentation, it says, do it. So, like I said, it's the preferred way that's not preferred. CPU sets, which to me are kind of a little bit more of a pain to do, but they say it's kind of more of a preferred way of doing it. You got to go through a whole series of things. Here's the directory where CPU sets are created. You have to echo CPU exclusive. If you want to make a CPU isolation, you got to make sure the top level CPU set has something exclusive. So I want CPU 1. This is CPU, or no, this is a flag on or off. So CPU exclusive is true. Then you make a directory within the CPU set directory, and then you could echo what CPUs you want to be isolated, and then you say this is exclusive as well, and then you could echo whatever task, like right here, $, I'm echoing bash to be exclusively in this. So that's how you make a CPU isolated way of doing things today. I don't know, maybe we'll have a utility to make it a little bit nicer than that. Config no-hertz. No-hertz is another thing that's great for your laptop battery life. And it's also great if you don't want to cut down on your AC. What no-hertz means is when the system is idle, it's going to turn off the timer interrupt. Because right now, usually if you see that hertz mode, a lot of 100 hertz is probably the slowest you can make your CPU cycle. Because every 100 hertz or 1,000 hertz or whatever, so every 10 milliseconds or 1 millisecond, an interrupt's going to go off and do timekeeping. It's going to make sure all your timers are up to date. It's going to look at your processes. It's going to make sure, like ever do that time a task and it tells you how much CPU time you took or how much time you're in the kernel, how much time you're in user space. That's done on a periodic basis by the hertz, once a second. Well, when the system is idle, it's kind of stupid to do this. And what happens is if you go off even at every 10 milliseconds, the CPU has to wake up and do something and go back. And the longer you keep the CPU from doing anything, the deeper it could go into sleep and the less power it will take. And you can have a really nice, long-lasting lifetime on your battery if you're not doing much. So no hertz is a great thing, especially for server classes that don't really require the determinism. But the deeper it gets, the more groggy your CPU gets. So which means is you could take 20 milliseconds just to wake up the CPU because it's almost powered off. So it's great for power savings, but if you want a reaction time, if that CPU is down and your task is on that CPU and it wakes up, you've got to power up the CPU and run it. So no hertz is great for power savings, sucks for real time. No hertz full is great for real time. What no hertz full is the same concept as what I said, where you're not doing anything. If you don't need a timer interrupt, don't one go off. Now, if there's one task running in user space, there's no calculation. Remember that RCU thing I said before? RCU knows that if something's in user space, it could ignore it. It doesn't need to do anything. So when you have that synchronized RCU, when it gets to a CPU that has something running in user space, it knows to ignore it. So you can have a task running full forever, never going into the kernel, and it shouldn't have any interrupts happening to it. So this is where you could do polling on a memory mapped register. If you want really quick fast times, a lot of people ask us for this. So no hertz full is great for that. One of the problems is, RCU needs to know that you're in user space. So that means we have a hook every time you go into the kernel, and every time you come out of the kernel, there's a hook there that says we're going into user space and we're coming out of user space. That wouldn't be there if you had this thing turned off. So if you want this enabled, you can have really nice speed, but it's going to slow throughput it down. And now, again, balance between real fast and real-time determinism. Again, you have to work with that. The application layer. I'm going to kind of skip the library layer. I'm going to more talk about your application layer. So when you come down to real-time tasks, make sure you're memory locking. The first time I ran that deadline test thing I got horrible results. And then I went, oh, crap. I forgot about mlock all. So everyone familiar with mlock all? If you're not, you should be, if you want to do real-time systems. What mlock all does is a way to tell the kernel, remember that paging we had there? We want things real fast. So when you run an executable, what the kernel will do is it won't pull in, it won't read the whole hard drive. If you start up, Mozilla, it's not going to read your entire binary Mozilla program. That's very large, and pull that all into memory. What it does is it basically tells the kernel that this virtual address space is going to be mapped to this file. So when you run your code, when it goes to execute that virtual address space isn't there. It will fault. And then they say, oh, we faulted. So what it does is it builds the page tables to point to, that's saying this virtual address space will equal this RAM. Well, first it's got a fault. It's going to go all the way down into your file, into the hard drive. It's going to pull the memory of that application from the hard drive into memory, set up the page tables, and then continue. So this is actually it's slow because at the beginning it's slow, but it also saves memory. It makes things execute quicker. You don't want to wait there forever, pulling everything when you're not going to use most of the binary or file. So mlock all is a way to tell the kernel, I don't want that feature. I want you to go to the hard drive right now and pull everything into memory. And if I'm going to, give me a heap, give me a stack, give me everything so I know how to use, so this will always be memory so I don't have to worry about page faulting. You want both current, which does all the thing current, and future will do the heap and stack and stuff like that. So those are flags passed to mlock all, so you get everything locked in. Now remember, this is a very scary feature. I always say real time is a gun to shoot yourself in the head with, because it allows you to do things that will kill yourself. For one thing is if you fill up memory, it's locked into memory. That means that you just pull stuff in memory that will not swap out. And your memory for everything else has just shrunk. If you do this enough, sooner or later, the mlock all will fail, but your whole system might fail because your programs won't be able to have any memory to load. Because once you do it, it's just like the kernel. The kernel memory is always, or the kernel code's always in memory. Now your application's always in memory. But it's great for real time. Priority inheritance. Locking. We have locking. I mentioned unbounded latency before. You always have bounded latency. Latency is simply when a bounded latency, or actually latency, priority inversion, sorry. Priority inversion is simply when you have one application that wants to run and another application that's higher priority, well, I should say, that's already, or say, lower priority that's running. So you have an application that's lower priority running, and a higher priority task wants to run. As soon as it wants to run, the latency between the time that it wants to run to the time it actually does run is called a priority inversion. Right there. It's impossible to get rid of. Otherwise, unless you had an interrupt that goes off and the guy could stop and just run immediately. Any gap there is a priority inversion. What we don't want is unbounded priority inversion. Unbounded priority inversion, I always love this graph. I think I show it in every single talk I ever give. I love this graph. I should talk about the Mars probe that went out and crashed due to priority inversion. Basically, you have three tasks, A, B, and C. Let's say A is the highest priority process, B is next, and C is the lowest priority process doing logging. C's going on, and it grabs some lock, and it gets preempted. A runs, and it goes and tries to grab the same lock that C has and blocks. So it goes back, runs, C runs, but before it can release the lock, it gets preempted by B. Now B is going to run, and let's say B is waiting for A to tell it to stop. See what happens? It never will happen because B preempted C, which happens holds A. And this actually happened on the Mars probe, if you can read about it, on the way to Mars. And the way they got around it was because of the great mechanics and what's it called? Geez, my mind's not working very well. It's the third day of the conference. It's time, horrible time to give a talk. What? Well, it's JPL, but I'm trying to think of redundancy. That's the word I'm looking for, redundancy. A redundancy in the system. It was able to monitor and see what, and they detected what happened. So what they did was they rebooted the box on the way there. So we did a full reset, and then started up, went through the whole thing, and then, okay, well, it takes a few months to get to Mars, so they had plenty of time to do it. Priority inheritance is the way that we solve it. What priority inheritance is that when A blocks on C, say C's running and has a lock and gets preempted by A. A goes and it gets preempted, or it hits the lock that it wants from C. What happens is at this moment, we give C the priority of A. So now C is running at a higher priority, temporary higher priority. So it goes to run. Now B wakes up, but because B is now lower priority than C temporarily, it doesn't preempt it. Now, when we release the lock, C will lose the priority, but now A's ready to run, it can run, goes, sleeps, and then B runs, and everything's happy. So, going back, we have that in support for pthread. That's how pthread prio inherit works. Task and interrupt thread dependencies. Like I've showed you, this is kind of like a repeat idea. You have to be aware of how your tasks interact with other tasks, and how your tasks interrupt with threads. And I said, I mentioned earlier that your CPU POSIX timer, if you're using that one thread or timer create, you got to make sure that this guy could run, and you don't starve it because your interrupt will never, or your timer will never wake up and run. So you need to be aware of how these things work. Work queues, you'll see work queue threads in the kernel. They do various kernel maintenance. And there's a lot of kernel maintenance and drivers that will use work queues, and if you starve them, those maintenance will not be done. Sometimes you got to understand what's happening in the system to know how you're going to modify things. So you always want things to be able to run and not block things for too long. And if you do, you better know what you're doing. So otherwise, you might have results that are not expected. My favorite is real-time versus multiprocessor. It seems like real-time has all these enemies out there. We have power-saving enemy. We have the real fast enemy. And now we have the multiprocessor enemy. Next, we'll have the Joker enemy. He's just cracking up on that. Whoops. Are you good? Yes. So migration, whenever you do that, all your caches are cleared. Once your task migrates onto another CPU, you start from scratch. You got to pull in all the caches, you're basically going into your worst case scenario again. So you got to be prepared for that. Now, RT tries to give you a best effort idea on how to migrate. So if you have a task that wakes up on another, like if you have an RT task that wakes up on a CPU that's running a higher priority RT task, or maybe an RT task that's the same priority, but it can't, but it's a FIFO, which means that it's got to wait for that guy to finish, and there's a CPU that's running non-RT tasks, is idle, or maybe even a lower priority task, the kernel will try to move that as much as possible. So if you kick off a bunch of tasks, sometimes people say, geez, I ran my program under real time and it slowed down tremendously. What happened? Well, I looked at the system and they have like 50 threads on 4 CPUs. And because real time versus like the real fast versus real time again, when on a normal non-RT task, a normal sched other process, what everyone your default scheduling class will be, because of us trying to preserve cache, preserve the page tables, preserve the TLB. What we will do is when your task is running and it schedules out, it's not going to migrate to another CPU, even if another CPU is idle. It's going to sit there, it's going to wait. It's going to wait a while, and periodically the kernel will wake up and say, oh, we got an imbalance. We should start moving tasks around. And it will start moving things around slowly, because if you have two tasks that are going back and forth, back and forth, back and forth, and they both are using their own cache lines and have their own TLBs, it's much faster. Just let them run than if you were to migrate it over, then something happens and I migrate it back. So bouncing tasks around is a very slow operation. But for real time, we're worried about how fast can it react. So we don't care about the slowness of moving a task around. But you got to be aware of that. So just because you made a task real time, suddenly it could slow down if it's bouncing around a lot. Because if, like I said, it's not going to do this preserve cache on your migration. It's going to just get you to run, hey, that CPU is available, run there. And then if you load up again, oh, that CPU is available, run there. And you'll see them bouncing around like crazy. SCHED-RR, round robin scheduling class, is something that you have to be careful about. We don't do migration of the same priority. And this is something that we thought about maybe we could fix somehow, maybe using the other scheduling class again. Say if you have two tasks running on CPU 1, single task running on CPU 2, both with the same priority, but if this guy wakes up on this one, these guys are going to share 50% of this CPU, and this guy's going to run at 100% of the CPU. This guy will never migrate back and forth. Ideally, they should all be using like 66% of the CPU and bouncing around nicely to keep everyone the same. But if you expect the kernel to do the migration for you, things like this can happen. Ideally, real-time tasks, you should have full control. You should be controlling the affinity of your tasks and not even letting it migrate. Sched deadline. As I mentioned before, there was a great talk earlier today. Did he come back in yet? I'm going to have to yell at him. So, everyone familiar with Sched deadline? OK. Here's a little idea of what you have. Let's say you have a machine that's going to run two tasks. This machine happens to be in a power plant, a nuclear power plant. And one of the tasks is making sure that the core is cool. And it must run 3 milliseconds every 5 milliseconds. Then you have this other machine attached to your computer. And this machine washes the rags you use to clean the nuclear power plant with. It's a washing machine. Same computer, one CPU. This task will run, it needs to run 150 microseconds every 500 microseconds. Now, if you do the calculations of percentage-wise, you're running about 95% of the CPU for doing two tasks. What do you give the higher priority to? Well, ideally, you think nuclear power plant, because if it doesn't make its deadline, bad things happen. If the washing machine doesn't make its deadline, you come up with dirty clothes. So, but if you do that and say, let's make the nuclear power plant running, your washing machine will fail every time, because when it runs for that 1 millisecond, the washing machine needs to run 150 microseconds every 500 microseconds. It's got a huge gap before it could run again, and it's going to crash. So your system sucks. Of course, you're going to fire the designer that thought of such a stupid idea of putting a washing machine with a nuclear power plant, but never mind. So the idea is you want the higher priority goes to the smaller frequency. Now, here's a problem with that. Like I said, we're using about 95% of the CPU. There's going to be a time where things are going to get just enough, like say if there's a little pause somewhere or something else comes in and we shift over, and now there's a frequency rate where, let's say that the nuclear power plant task needs 20 microseconds left to run. Or say it has 50 microseconds left and it has 20 microseconds that it needs to execute. But the deadline's in 50 microseconds. But then the washing machine wakes up and it runs for 150 microseconds. Hello Chernobyl. It will crash the power plant. So the whole idea of earliest deadline first is the fact that it's a dynamic priority. You see who has the next deadline, and that task runs next. Someone, I can't remember his name. He is probably here. I'm going to use this example. It's a great idea. It was a great analogy. I took his picture of his badge, too, to remember it. Wait, there he is. What's your name again? George. George over there. He said it. He knows exactly what I'm talking about. He gave a great example of this whole idea. When you're on an airplane and you land, airplane that's delayed, no one ever had that. And you come down and you look at whose flight is next. Let them off first. That's the thing, dynamic priority. Not the person that's up front. No, this guy in the back of the plane, his flight is in 15 minutes. He's got to cross 4 terminals to get there. You let him off first. Okay, that's the idea of earliest deadline first. Great analogy, by the way. And to be continued means that that's probably ELC EU. If you go to Europe, I'm planning on maybe talking more about that. Questions? Yes? Wait, you got to either talk on the mic or I got to repeat your thing, and I'd rather not. You're the one supposed to run back and forth and get the mic. We already assigned that. Yep. See, it says 50, real time. Real fast.
I'm surprised to hear you talk about situations where some threads get starved, because I thought there was the sched_rt runtime that sort of kicks in and will kick out a task even if it's a high priority. And
the K-soft area, the tasks that are getting starved are RT tasks. Okay. So the question was, there is something that's a default operation. On RT systems, I tell people to turn that off. We have a mechanism to keep, because most systems are not real-time systems, so ideally if you go into your proc sys kernel directory, /proc/sys/kernel, you'll see files in there about like sched_rt runtime, sched_rt period. All RT tasks have kind of a periodic deadline thing where it will run 0.95 seconds every second. It's allowed to run that. If it runs more than 0.95 seconds, it was going to stop it and allow that 0.05 seconds to for other tasks to run. That way, if you have a runaway RT tasks that can lock up your system, it allows you to get in and kill that RT task. It'll be slow, but you could get in there. The problem is with the starvation is that stops all RT tasks. It's a global stop RT task to let non-RT tasks go. The starvation happens is you have an RT task spinning, and the other task that wants to run are also RT tasks. So they're blocked as well. So you're right. It's spinning. You'll get this 0.05 seconds stopping time. That's how we were able to see, monitor. We actually were able to get in and say, what's going on here? Why is the thing existing? But then if we did something that did a sched or RCU, or synchronized RCU, it blocked too.
Yeah, I didn't find it because I read about it. I found it because it came up.
Yeah. Any other questions? Yes, over there. You want to run over there?
Can you elaborate a little more on
Put closer so I get here.
Yeah, can you hear me?
Yep.
Yeah. Can you elaborate a little more on the branch predictor case? So what was your test program? Because the variations you seem to get were from 100,000s to millions all of a sudden.
Okay, the test program, like you said, you could actually go to github/Rostedt/sched_deadline.git. Okay, that's where my test program was. And I also compiled the kernel with branch profiler enabled, which basically does tracing on every single branch in the kernel. So that's where I have define if.
Okay.
If you know any C programs in here? You guys program C? Yes. Oh, you did that? You showed the slide with the define if? Yeah. I have a thing where I have define if, boom. So I actually redefined the if statement in C. And I had that enabled. That causes a lot more branches, and that's why I was blowing away branches.
Okay, all right. Yeah. Thank you.
Over here?
Would you recommend to disable overcommitting, memory overcommitting? Because I saw interesting things happen if you run out of memory, of course.
What, memory overcommitting? Well, no, ideally, no, I don't care about a memory overcommitting. Yes, you only care about the RT tasks being predictable. You don't care about the non-RT tasks being predictable.
The RT task gets stalled if the
That's why you do the mlock law. When you start to do it properly, as a proper system, the real-time task should already reallocate all its memory. There should be no malloc or allocation done while that task is running.
I'm not sure what exactly happened, but as soon as the OOM killer kicked in.
Oh, OOM killer, I see. Yes. Okay. Yes, that could happen. Yeah, you're right. You're unpredictable things. If you run out of memory and the OOM memory comes in, does it will pick a memory lock thing? Will it pick the real-time task?
I think it disables the whole scheduler.
Yeah,
I
yeah.
don't know. what
I would
it's-
recommend, okay, yes, I would recommend, for that case, yeah. Make sure you didn't. But right now, that means you're having a system that has, even your non-real-time tasks. Like I said, it's not just about the kernel, it's not just about the tasks, it's also about the hard, it's about the entire system. If you have something in there that's doing that, you should fix that guy. That guy should, the overcommit should never have happened. That means your system has a flaw. But you're right, if you don't want to, but still, if you're hitting that, there's something wrong with your system. Make sense? Any other questions? Okay, well, you get one more question real quick. He can wait. Yeah, one question, go.
Okay, I have a question. You were talking about work queues. Do you think the
What?
work queues?
Work queues?
Yeah. Do you think we should be a bit more granular regarding the work queues? Because I know a lot of drivers are just picking up, the default work queues that are made for you.
Wait, what about the work queues? What's,
I mean, a lot of drivers are actually using the default work queues.
yeah,
Maybe we should just create
because most of the
one work
drivers,
queue for each driver.
only if you care about if those drivers you need for the real-time tasks, you have to be careful about. But a lot of times they don't need. And if you're using work queues, a lot of times you have to monitor. You have to actually audit the drivers that are required for the real-time tasks. There's work queues that are being used that you don't care about. Drivers you don't care about. But if there's something like the networking stack doesn't really use work queues. And a lot of times we worry about networking stacks, or if you have a device that you're like a sensor, do sensors use work queues? Yeah. Or do they use interrupt threads? If you use interrupt threads, we recommend actually interrupt threads possible, if you can.
Yeah, right.
But yeah, so that's it. So thank you very much. Appreciate it. And see you at ELCEU or earlier.